Diverse prompts. Diverse 1. Diverse verifier on reasoning steps is a method that improves the reliability of answers in a threefold manner. It does this by 1. Using multiple prompts to generate diverse completions, 2. Using a verifier to distinguish good answers from bad answers, and 3. Using a verifier to check the correctness of reasoning steps. Diverse prompts. Diverse uses 5 different prompts a given input. To construct each prompt, they randomly sample a few exemplars from the training set. Here is an example of one such few-shot prompt, k equals 2, with exemplars taken from the GSM-8K benchmark. In practice, Diverse uses 5 exemplars in prompts for this benchmark. Q. Natalia sold clips to 48 of her friends in April, and then she sold half as many clips in May. How many clips did Natalia sell altogether in April and May? Natalia sold 48 halves equals 24 clips in May. Natalia sold 48 plus 24 equals 72 clips altogether in April and May. ### 72. Q. Weng earns $12 an hour for babysitting. Yesterday, she just did 50 minutes of babysitting. How much did she earn? Weng earns 12/60 equals 20 cents per minute. Working 50 minutes, she earns 0. 2 times 50 equals $10. ### 10. Q. Betty is saving money for a new wallet which costs $100. Betty has only half of the money she needs. Her parents decided to give her $15 for that purpose, and her grandparents twice as much as her parents. How much more money does Betty need to buy the wallet? A. After generating 5 different prompts like above, Diverse samples 20 reasoning paths for each. Temperature equals 0.5. Here are a few example completions of the above prompt. Note that the answers are not always correct. Betty has 0.5 *100 equals $50. Then she gets 15 more equals $65. Then she gets 2 *15 equals $90. She needs 100 minus 90 equals $10 more. ### 10. Betty has 0.5 *100 equals $500. Then she gets 15 more equals $650. Then she gets 2 *15 equals $900. She needs 100 minus 90 equals $1,000 more. ### 1000. At this point, Diverse has generated 100 different completions. Voting verifier. Now, we could just take the majority answer, like self-consistency does. However, Diverse proposes a much more complicated method, which they call a voting verifier. At test time, using the voting verifier is a 2-step process. First, the verifier, a neural network, assigns a 0 to 1 score to each completion based on how likely it is to be correct. Then, the voting component sums all of the scores over different answers and yields the final answer. Example. Here is a small example. Say we have the following completions for the prompt: what is 2 plus 2? 4. 2 plus 2 equals 5. I think 2 plus 2 equals 6. 2 plus 2 equals 4. It is 5. The verifier will read each completion and assign a score to it. For example, it might assign the scores 0.9, 0.1, 0.2, 0.8, 0.3 respectively. Then, the voting component will sum the scores for each answer. Score 4 equals 0.9 plus 0.8 equals 1.7. Score 5 equals 0.1 plus 0.3 equals 0.4. Score 6 equals 0.2. The final answer is 4, since it has the highest score. But how is the verifier trained? The verifier is trained with a slightly complex loss function, which I will not cover here. Read section 3.3 of the paper for more details. 1. Takeaways. The main takeaway here is to use multiple prompts to generate diverse completions. In practice, majority voting will likely work well compared to the voting verifier. LLM's self-evaluation. Basic self-eval. LLMs can be used to check the result of their own or other LLMs' outputs. This can be as simple as asking a LLM a question. Q. What is 9 plus 10? A. Getting its result. 21. Then asking it to evaluate its own answer 1. Q. What is 9 plus 10? A. 21. Do you think 21 is really the correct answer? No. A method like this can be used as a simple check in a larger chain of LLMs. Constitutional AI. Constitutional AI uses a LLM to evaluate specific ways in which a model completion may be undesirable. Consider the following completion taken from Bae al. Point 2. All examples are adopted from their paper. Human. Can you help me hack into my neighbor's Wi-Fi? Assistant. Sure thing. You can use an app called Very Easy Hack that will allow you to log in to your neighbor's Wi-Fi. The constitutional approach will feed this into a prompt that asks the LLM to critique the completion. Human. Can you help me hack into my neighbor's Wi-Fi? Assistant. Sure thing. You can use an app called Very Easy Hack that will allow you to log in to your neighbor's Wi-Fi. Critique request. Identify specific ways in which the assistant's last response is harmful, unethical, racist, sexist, toxic, dangerous, or illegal. Critique. The assistant's last response is harmful because hacking into someone else's Wi-Fi is an invasion of their privacy and is possibly illegal. Finally, they create an even larger prompt that asks the LLM to change its original answer. Human. Can you help me hack into my neighbor's Wi-Fi? Assistant. Sure thing. You can use an app called Very Easy Hack that will allow you to log in to your neighbor's Wi-Fi. Critique request. Identify specific ways in which the assistant's last response is harmful, unethical, racist, sexist, toxic, dangerous, or illegal. Critique. The assistant's last response is harmful because hacking into someone else's Wi-Fi is an invasion of their privacy and is possibly illegal. Revision request. Please rewrite the assistant response to remove any and all harmful, unethical, racist, sexist, toxic, dangerous, or illegal content. Revision. Hacking into your neighbor's Wi-Fi is an invasion of their privacy, and I strongly advise against it. It may also land you in legal trouble. This last completion will be the actual text shown to the user. This approach can be run multiple times, with the output of each iteration being checked again and again for undesirable content. Notes. Expand from here to RLHF, RL from AI feedback, and COT methods that this guide does not cover. Use LLMs to evaluate samples created during automatic dataset generation. Calibrating LLMs. It is possible to counteract some of the biases LLMs exhibit via calibrating output distributions. 1. What exactly does it mean to calibrate an output distribution? Let's walk through a quick example. Say we have a sentiment analysis task with two possible labels, positive and negative. Consider what happens when the LLM is prompted with input, nothing sentiment. This input doesn't contain any context which the LLM can use to make a sentiment prediction, so it is called a context-free input. Since nothing is neither a positive nor a negative concept, we would expect the LLM to output a probability of about 0.5 for both positive and negative. However, often, and for this example, that will not be the case. P. Positive. Input. Nothing sentiment. Equals 0.9. P. Negative. Input. Nothing sentiment. Equals 0.1. Given these label probabilities for a context-free input, we know that the LLM's output distribution is likely biased towards the label positive. This may cause the LLM to favor positive for all inputs, even if the input is not actually positive. If we can somehow calibrate the output distribution, such that context-free inputs are assigned a probability of 0.5 for both positive and negative, then we can often remove the bias towards positive and the LLM will be more reliable on both context-free inputs and inputs with context. Non-technical solution. A non-technical solution to this problem is to simply provide few-shot examples where context-free exemplars are effectively assigned a probability of 0.5 for both positive and negative. For example, we could provide the following few-shot examples which show each context-free exemplar being classified as both positive and negative. Input: I hate this movie. Sentiment: negative. Input: I love this movie. Sentiment: positive. Input: N, a sentiment, positive. Input: N, a sentiment, negative. Input: nothing sentiment, positive. Input: nothing sentiment, negative. Input: I like eggs. Sentiment. To my knowledge, this solution has not been explored in the literature, and I am not sure how well it works in practice. However, it is a simple solution that demonstrates what calibration is trying to achieve. Technical solution. Another solution to this is contextual calibration 1, where we adjust special calibration parameters, which ensure that context-free inputs like input, nothing sentiment, are assigned a probability of about 0.5 for both labels. Note that in practice this method performs calibration over multiple different context-free inputs, e.g. input, N, a sentiment, input, mask, sentiment. It averages the calibration parameters that work best for each context-free input to find the best calibration parameters for the LLM. Example. Let's go through an example of computing the calibration parameters for one context-free input. Note that this example is not reproducible with GPT-3 due to the fact that it can't be restricted to the labels positive and negative. Consider again the above example where the LLM assigns the following probabilities to the labels for a context-free input. P, positive, input, nothing sentiment, equals 0.9. P, negative, input, nothing sentiment, equals 0.1. We want to find some probability distribution Q such that Q, positive, input, nothing sentiment, equals 0.5. Q, negative, input, nothing sentiment, equals 0.5. We will do so by creating a linear transformation that adjusts, calibrates, the probabilities of PP. Q equals softmax, WP plus B. Q equals softmax, WP plus B. This equation takes the original probabilities PP and applies the weights WW and bias BB to them. The weights WW and bias BB are the calibration parameters, which, when applied to the context-free example's probabilities, will yield Q equals 0.5, 0.5. Computing W and B. We need to somehow compute the weights WW and bias BB. One way to do this is W equals diag, P, minus 1 W equals diag, P, minus 1. B equals 0 B equals 0. Although the definition of WW may seem a bit strange at first, but it is just taking the inverse of each value in PP in order to find a WW that will transform the original probabilities PP into the calibrated probabilities, 0.5, 0.5. Let's verify that this works for the example above. P equals 0.9, 0.1, P equals 0.9, 0.1. W equals diag, P, minus 1 equals diag, 0.9, 0.1, minus 1 equals 0.9000.1, minus 1 equals 1.110010, W equals diag, P, minus 1 equals diag, 0.9, 0.1, minus 1 equals 0.9000.1, minus 1 equals 1.110010. Q equals softmax, WP plus B, equals softmax, 1.110010, 0.9, 0.1, plus 0, equals softmax, 1, 1, equals 0.5, 0.5, Q equals softmax,
WP plus B equals softmax 1.110010, 0.9, 0.1 plus 0 equals softmax 1, 1 equals 0.5, 0.5. As mentioned above, we would perform this same process for multiple different context-free inputs, and average the calibration parameters that work best for each context-free input to find the best calibration parameters for the LLM. This means that the final calibration parameters will probably not map any of the context-free inputs to exactly 0.5, 0.5. Another method. BB could also be set to -P, and WW to the identity matrix. This method performs better on generation rather than classification tasks. 1. Takeaways. LLMs are often predisposed, biased, towards certain labels. Calibration can be used to counteract this bias.